Okay, so we're going to go over chapters 12 and 13. It's over solids, liquids, and intermolecular forces. Okay, so the first thing I want to talk about is the three different states, molecular comparisons. This is just basically just a review of stuff, but what we want to look at here is the intermolecular attractions right there. Okay, for solid, the intermolecular attractions are stronger, and that's why they're closer together. Okay, liquid is the middle, gas is the weakest. That's why they can be so far apart. So these are intermolecular attractions. What's holding one molecule to another molecule? Okay, so for example, here we looked at gas and we said gas was a weak intermolecular attraction, so they're far away. Liquid is closer, and solid should be the closest. Now, this obviously is an exception because water, for H2O, the liquid phase is actually going to be packed tightly compared to ice. That's why ice floats. But it's only a really small difference here. It's 0.917 to 0.998. But it's really because water is closer to 1 and ice is actually a little bit less dense than that. But this is an exception, okay? And most of the time, solid is packed close together, liquid is in the middle, gas is the furthest apart. So the further apart they are, the weaker the intermolecular attraction, okay? So we'll talk about that. So under solids, we talked about how there's amorphous solid in chapter 1 or 2, and then we have crystalline solids. So crystalline solids are the ones that have long range order in 3 dimensions, okay? Amorphous has no order, it's just basically they're all over the place. There's no order. So they gave you an example. Salt and diamond are crystalline, amorphous are like plastic and glass. So, and then we have liquid and gas. Now, liquid and gas, you can change the phase from liquid to gas by heating up the temperature, right? Heating it up, raising the temperature, or you can change it by manipulating the pressure. When you have gas, you squish it down, increase the pressure, and make the volume really, really small. You can actually squish the gas. Eventually, it can turn into liquid, okay? So that's right here. Oh yeah, and then it says here, gas can be compressed, liquid is not as easily compressed. I mean, I guess you could, yeah, it's really common to compress gas, but not for liquid. So in this case here, remember, we can work with heat, or we can also work with pressure to change phases, okay? And like, for example, here we have propane tanks here, and inside the tank, it's in liquid phase, but then when you release it, we have it in gas phase because we control the pressure change. So what's holding these guys together? We talked about intermolecular attractions, right? So let's discuss this. There's particles in there, either atoms, molecules, whatever it is. They are basically attracted to each other. So I just do like models or something. So this one here, whoa, sliding all over the place. Anyway, okay, never mind. So these two like this, they're particles, and when they're close together like that, okay, that means it is in solid phase, right? When it's close together, okay? Now, when you put them a little bit further apart, they say, okay, now it's liquid. And even further apart, it's gas. So the point is, what can you do to break them apart to change phase? So this is solid, and then bring it out further is liquid, and then bring it out even further, it's gonna be gas. So what does that? So every single kind of molecule or particle, atoms, whatever, they have some sort of attraction to each other, okay? So this is called intermolecular attraction, and we have different kinds. And depending on what kind they are and how strong they are, you can tell how easily this can be broken apart, so you can make them into liquid and gas phase. So we want to talk about these different kinds of intermolecular forces, okay? So it says here, the higher, so boiling a liquid requires that we add enough energy to overcome all the attractions. We have to break them apart from each other, but not actually breaking the actual bond. Like say for water. I'm trying to make water. Well, I take some of water molecule. Here's a water molecule. So we have one water, we have another water floating around. I'll make it up. Okay, so we have one water and another water. And to make it, okay, so we have, when the waters are together, maybe when they're close together, that's like, liquid phase. And then when you want to break them and move them really far away from each other, they become gas phase. But did you change the molecule, the covalent bonds in there? You did it, okay? So you got to remember, intermolecular force is just one compound talking, one molecule talking to another molecule like that, without changing these bonds there, okay? So it doesn't change the covalent bond. Okay, so the weakest intermolecular force is the force that everybody has. Okay, it's called the London dispersion force or van der Waals. Van der Waals here says that basically everybody that has an electron can have London dispersion. Remember we talked about electrons saying it's an orbital, and it's we kind of know the orbitals are probability density of what electrons are, so they're always moving all around that orbital here. So this is just basically saying, okay, here's neons, electrons, but they're going to be floating all around this guy. They're free float. We don't know where they are. We don't know how fast they're going. We know one, but not the other. So it's uncertain, right? But anytime you have multiple of these atoms together of neon, at some point, you might get a one split, small, tiny split millisecond or femtosecond. You get the electrons line up on one side and the other one lines up on the other side too. Like they kind of just have a split second order, okay? Where the electrons all line up on the top here, and the next guy electron lines up on the top. But then because they're free flowing all the time, that attraction there only lasts for a second, because when it lines up to one side, that means this side is the negative polar, negative side of the atom, and this side is the positive, and then this side is the negative side, and that's the positive. So the negative is attracted to the positive. So they kind of have an attraction there, but the attraction is temporary. It's not permanent, because after electrons move around, they disappear. Okay, so it's very random. So they're attractive forces caused by temporary dipoles. Why temporary? Because the electrons are always running around free. Okay, but they do have it. So anybody that has electrons will have London dispersion force. So I guess, you could say the more electrons they have, the more London dispersion they can be. Okay, so this is a temporary induced dipole that causes the London dispersion force. Now remember, dipole in a dipole moment here means that, this dipole moment is points to the negative side. So this side will be negative. The side with the electron is the negative side, if it lines up, but in this picture it's not lined up right now. Okay, so that is London dispersion force. So who has London dispersion? Everybody has London dispersion. So how can we judge them? Basically, the heavier they are, the larger molar mass will have more electrons. Then you can arrange them, have a bigger temporary induced dipole. So they'll have stronger intermolecular force here. So when you want to judge London dispersion force, number one, you take a look at the molar mass. Okay, the bigger molar mass here, you can see nonane is C9H20 versus pentane is C5H12. It's much, much higher boiling point. Now, why do we say a higher boiling point means stronger intermolecular force? In this case, stronger London dispersion, because the London dispersion is what holds one molecule to another molecule like that. They line up. And the more electrons you have, the better, the stronger the connection will be. Okay, so something that's heavier will have a higher intermolecular force. And because they're strongly attracted to each other or stronger in comparison, it's going to be harder to break them apart to turn them into gas from liquid phase. And that's why the boiling point is higher for nonane, and the boiling point for pentane is going to be lower because this one has a lower molar mass. So less electrons to line up, the temporary induced dipole is weaker than what you would have in nonane. Okay, so because it is weaker for pentane, then it'll be easier for you to remove one pentane molecule from another pentane molecule, and then they can turn them into gas phase with less energy. So therefore, the boiling point will be lower because you don't need a high temperature to get there. Okay, because the temperature will give it more energy. When you pump up the temperature, the energy increases. So, and then we can also take a look here. If you want to take a look at noble gases, molar mass are increasing as you go down the group, and you can see the boiling point increases as well. And that has to do with this. The bigger ones here have more electrons, and then it'll be harder to peel one xenon from another xenon than it is from helium to helium, because the clouds are bigger for xenon, electron clouds. Okay, so that's a temporary induced dipole, judging it using molar mass. And then if the molar mass was the same, if you had something with the same molar mass, then you want to consider the shape. Something that is long like this, like a long chain, will have more electrons that can line up compared to something that's branched and has a very small contact point to line up. Okay, so something that has a long straight chain, even though the molar mass is the same, for this case, both of them are 72, the one with the straight long chain is going to be higher intermolecular force, in this case, London dispersion. Higher stronger London dispersion for N-pentane compared to neopentane because of the electron cloud being able to align in a long chain there. Okay, so that is the weakest intermolecular force, and anyone who has electrons will have it. Okay, so that's the first one and the most common one, because anything with electrons can have London dispersion force. The bigger the molar mass, the higher the London dispersion force. And when you comparing shapes, if it's the same molar mass, something that's branched will have a lower boiling point because it has less smaller London dispersion force. Okay, now the next force that we want to talk about is called the dipole-dipole force. The difference between dipole-dipole and London dispersion is dipole-dipole has a permanent dipole on the molecule, permanent. Before this, London dispersion was just split-second dipole that's induced, and then it disappears. This one here, the molecule is permanently dipole, and that's why it was so important from the previous chapter that we learned to recognize whenever a molecule is polar, depending on the bonds and how the bonds are arranged in a geometry. Okay, so some molecule that has polar bonds, but the polar bonds cancel each other out due to geometry, overall is nonpolar, and those nonpolar guys will not have dipole-dipole force. They will only have London dispersion. Okay, so who has dipole-dipole force? Only molecules that are polar. So the molecules must have polar bonds and the bonds don't cancel each other out, and then they have a permanently negative side, permanently positive side, and then they line up. Okay, so this is dipole-dipole interaction here. So only polar molecules have dipole-dipole force here. So because dipole-dipole is permanent, this is stronger than London dispersion. London dispersion is a temporary thing, right? This is permanent. So dipole-dipole is a stronger intermolecular force than London dispersion. So polar molecules will always have higher boiling point when compared to a molecule that doesn't have polarity in it, that doesn't have dipole-dipole, okay? So the second one in the line is dipole-dipole is stronger. Anything that has dipole-dipole will have a higher boiling point, higher melting point, because it's going to take more energy for you to break them apart. Well, break the intermolecular forces. Okay, so an example here, formaldehyde is like this, and then you have ethane that looks like this. So remember we said CH and CC are nonpolar bonds. So this is, the whole thing is nonpolar. Look at the molar mass is exactly the same. So in this case, ethane here only has London dispersion force, and formaldehyde here has CO, this is a polar bond, nonpolar. So the bond is, the molecule is negative on the top, positive on the bottom. This one here has a permanent dipole. Therefore, formaldehyde has London dispersion forces, and it also has dipole-dipole force. Ethane only has London dispersion force. Because of this, you can see formaldehyde has much higher values in melting point and boiling point compared to ethane, okay? So, and then they show you examples here too. So this here is boiling point of different polar molecules, and they arrange the polar molecules according to how polar they are. The stronger the dipole moment means the more polar, more ionic character. They arrange it, and you can see the more polar it gets for the molecule, the higher the boiling point, because the dipole-dipole forces are stronger. Okay. Now, and then we want to talk, while we're talking about polarity, remember like dissolves like. So polar stuff will dissolve in polar, will mix with it, but you cannot mix polar and nonpolar. Nonpolar can mix with nonpolar, but you have to have the same type of polarity for it to be able to mix, okay? So in this case here, we have some questions. It says, here, which of these molecules have dipole-dipole forces? So my first question is, which of these molecules have London dispersion force? And your answer should be, everybody has London dispersion forces. But now let's consider which of these guys have dipole-dipole force. So how do you tell? Well, you have to be able to tell if the molecule is polar or nonpolar. Okay, so to do that, you have to remember what CO2 look like in shape, what CH2Cl2 look like. We've drawn this in CH4. Okay, so I wanted to show you what they look like in geometry now. So over here, we drew these guys in the previous chapter. So take a look at your own notes if you forgot. But based on that, okay, you can see that carbon dioxide, when you draw them out, is a double bond on each side. And because they cancel out, carbon dioxide is not polar, a non-polar molecule. Therefore, carbon dioxide does not have dipole-dipole. It only has London dispersion. Okay, now CH2Cl2, remember we just take the CH4, and that one's nonpolar. So all CH4 is nonpolar. So that one here is no dipole-dipole. But this guy here, all you do is you take two of the H's and replace it with Cl, and that's what happened here. Okay, so when you have that, C and Cl here, these are polar bonds. So this side is permanently the negative side of the molecule, and that side is the positive side. So this one has a permanent dipole. Therefore, there's dipole-dipole force for CH2Cl2, which is ethylene chloride here, or dichloromethane. Okay. So and then we have CH4 here. Note because CH4 is tetrahedral and they're all the same bonds. They're all nonpolar. So this guy's nonpolar, so it only has London dispersion. Okay, so remember, we got to go back and you have to remember what the shapes look like based on what we drew for Lewis dot structure. So here's another example. It says, which molecules have dipole-dipole force? Now, again, everybody has London dispersion, but not everybody has dipole-dipole because only the polar molecules will have dipole-dipole. The CI4 have dipole-dipole force. Remember, CI4 will look exactly like CH4, and you're all going to be pulling in equal opposites. So this guy here is going to be non-polar, so no dipole-dipole, only London dispersion, okay? And then same thing you can say for CF4. You could draw the same picture, or CBr4, because they're equal, they'll all cancel out, okay? Now CH3Cl, that means it's gonna look kind of in between this guy and that one, where only one of them is a chlorine, the other one was a hydrogen. So in that case, yes, it would be polar because like anytime there's that one green there, that guy will be the negative side and everybody else is the positive side. So CH3Cl here will be a polar molecule and therefore will have dipole-dipole force. HCl will also have dipole-dipole force because it's hydrogen and chlorine is just one bond, and that electronegativity between chlorine and hydrogen is really different enough because they're on opposite ends. They are going to be polar. Okay, so this one also has dipole-dipole force. All right, so there's another category that's similar to dipole-dipole, but it's strong. So we call this dipole-dipole on steroids. Okay, hydrogen bond is dipole-dipole on steroids because it's the strongest version of dipole-dipole. So who is hydrogen bonding? It's only for these guys, OH, NH, and FH. You guys remember how they say like the DNA is the double helix is because of hydrogen bonding? Well, this attraction here literally like is your genetic makeup, kind of the key to you. Like you literally are made out of just atoms and molecules and hydrogen bonds, kind of, a lot of it anyway. Okay, so just want to keep that in mind. So O and H is one, NH and FH. So I want to show you the periodic table. Basically, NOF bonded with H. Okay, those are the guys that will have hydrogen bond because they're super strong type of polar bonds. We just gave them their own category called hydrogen bonding. Okay, it's a really, really strong, even stronger than dipole-dipole. So if anything that has hydrogen bonding, it's going to be way higher boiling point than anything that just had dipole-dipole or London dispersion. Okay, so let's take a look at how hydrogen bonding can affect things. So in this case here, we have ethanol, which has hydrogen bonding, and dimethyl ether, which will not have hydrogen bonding. Okay, so if you can't really quite tell, see how this is an O and H here? So ethanol has an OH here, and that makes it a hydrogen bond attraction right there. Okay, so ethanol has hydrogen bond. The boiling point and melting point will be a lot higher for ethanol compared to something that doesn't. See how the molar mass is the same? Because this guy is arranged so the O is in the middle, it's not attached to an H. So there's no hydrogen bond because the options are OH, NH, or FH. Okay, and now you have CH and O. So the O has to be stuck to an H for it to have hydrogen bond. This one doesn't have hydrogen bond. This one has dipole-dipole though. Okay, it has dipole-dipole. This one has hydrogen bonding, and hydrogen bonding is a lot stronger. So you can see the boiling point for the one with hydrogen bonding is going to be higher, and so is the melting point. Okay, so hydrogen bonds are stronger, really, really strong intermolecular force, stronger than dipole-dipole or London dispersion. Anything with hydrogen bonding will have higher boiling points and melting points. But as strong as hydrogen bond is, nowhere near as strong as the chemical. Because remember, although we call it a bond, it's really force, okay? It's intermolecular forces. So this guy here, this is water, right? Water is O and H, so these guys have hydrogen bond. So you see how the negative side is always attracted to the positive side like that. They always kind of line up, okay? And we are not talking about, we're saying, yeah, this is hydrogen bond, it's strong and we can separate them apart. But to actually break that bond, it's nowhere near close in strength because hydrogen bonding is only 2 to 5% of covalent bonds. Okay, so intermolecular forces are really weak compared to actual covalent bonding or ionic bonding. Okay, so just keep that in mind. So there's your water right there. So we have 3 types so far. We have London dispersion, and then the next up is dipole-dipole, and then the next up is hydrogen bonding. So you have to remember what categories they are and who's the strongest. And then of course, I just showed you the molecule, and I'll just show you a picture of water. It's kind of cool how they line up. So I want to show you an example of how this can be applied. So take a look at this here. So this is group 6 bonded with group 6 and group 4. Okay, so this is oxygen, sulfur, selenium, and tellurium. So if you take a look here, that's group 6 right here. Oxygen, S, oh, you can't see. O-S-S-E-T-E, okay? And then they have carbon, S-I, I think it's G-E and S-M they have down here, okay? So as you go down a group, obviously it's getting heavier. So it's increasing molar mass. So this guy here for group 4, it's going to increase in boiling point because it's getting heavier. However, this guy here is getting heavier over here from S to SE to TE, but O for water is so much higher. Why? Because this one has hydrogen bonding. Okay, so sometimes I'll ask you, why is water's boiling point so much higher than H2S, H2SE, and H2TE? Well, it's because H2O has hydrogen bonding and the others don't. The others are just basically increasing in molar mass. Okay. All right, so let's keep going. Let's take a look at hydrogen bonding here. So the question is, they all have similar molar masses, okay? And the question is, out of these guys, one of them is liquid at room temperature. Which one and why? So liquid at room temperature means it's not boiling at room temperature, and the other guys are going to be boiling. So they're weaker intermolecular force, okay? So the one with hydrogen bonding would have a higher boiling point, so it stays liquid. So you just look for the one with hydrogen bonding, basically. Does this guy have hydrogen bonding? No, although the molecule has CH and O, but the O and H are not stuck together. So no, this one only has London dispersion and dipole-dipole. What about this guy? Does this guy have hydrogen bonding? No, this guy has London dispersion and dipole-dipole, but the F and H are not stuck together, so there's not hydrogen bonding. Hydrogen peroxide, though, it does have O and H stuck together. So this one here is going to have hydrogen bonding. So this is the guy that will be liquid at room temperature, and the other two will be in gas form. Okay? So they basically explain that here. They say it's because one has hydrogen bonding and the others don't. Okay? All right, so for practice, it says, which one has a higher boiling point, HF or HCl, and why? Well, in this case, HCl and HF has hydrogen bonding, right? So HF would have a much higher boiling point, even though HCl is heavier. All right, so now that we've talked about the three different kinds of intermolecular forces, there's a type of intermolecular force for mixtures of in this case, dipole and ions, okay? So polar molecules and ionic compounds here. So where you have, like, for example, you have NaCl, the Na plus ion is going to be attracted to the negative side of water right there. And then the positive side of water is going to be attracted to Cl. This is called ion-dipole force. Ion-dipole force is actually stronger than hydrogen bonding, but hydrogen bonding is the strongest out of the list for pure stuff. Pure means there's not two things mixed together. This one here, there's two things. There's ionic and there's water, right? So that one's a mixture. Ion-dipole is strongest, but usually since we're comparing just molecule to molecule without looking at it in water, we actually consider hydrogen bonding as the strongest when we're comparing. Ion-dipole only exists for dissolving salt in water typically, okay? So let's do a quick summary here. The summary is we have strength-wise, this London dispersion, dipole-dipole, hydrogen bonding, ion-dipole. This one is for mixture. These three are for pure stuff. And this is for everybody that has electrons. This is only for polar molecules. This is for molecule we have HF, OF, and NF. Okay? So the higher the intermolecular force strength, the stronger they are, the higher the boiling point and the melting point will be. So now that we talked about that, let's talk about some properties of liquids. Okay, so we're talking different phases. Now let's focus a little bit on liquids. Because we had a whole chapter on gases, and then next chapter 13 is on solids. So we want to talk about liquids now. So for liquids, we want to talk about surface tension. So surface tension is the reason why there's like little bugs that can walk on water, right? So it's kind of cool, and you're like, well, okay, why am I studying this? So let's take a look at the molecular picture. So the reason why we want to take a look at this is surface tension can actually be judged by how strong the intermolecular forces are. So when you have a sample of, like in this case, whatever molecules, maybe like a liquid, maybe water, I'll just pretend it's like water. And then on the outside here, the top layer, the water doesn't have any friends to align with. The inside molecules are all like, oh, look, I have a friend on this side, a friend on that side, a friend on that side. They're all like really well connected. And when they're connected like that, they're stable. Interior molecules interact with more neighbors, so they're stable. And the surface molecules only has neighbors down below it, but nobody above. Okay, because it's missing those neighbors on the top to help stabilize it, to bond it together, it has higher potential energy and is less stable. And this is why the molecules on the surface will try to minimize its occurrence. They're like, well, we're not stable. We rather go be on the inside. So everybody tries to going and be on the inside. So the tension, surface tension is basically how much energy do you need to increase the surface area, because the tendency for this guy is to want to decrease the surface area. Okay, so basically how much energy do you need to push in to splat that little round droplet of, maybe in this case, water. Okay, so we want to take a look at that. So they tell you surface tension is related to the intermolecular forces. Something that has hydrogen bonding has a much higher surface tension than something that doesn't have hydrogen bonding. This one here, C6H6 is all nonpolar. This one only has, benzene here only has London dispersion. Water has hydrogen bonding. So water is going to have a much higher surface tension. Okay, so surface tension is the energy required to basically break the molecule trying to decrease it, so increase the surface area. I just like to think of it as a droplet and how much energy it takes for you to squish it, something like that. Okay, anyway, so that surface tension has to do with intermolecular forces. So the next thing we want to talk about that has to do with intermolecular forces is viscosity. So viscosity is resistance of liquid to flow. So the more viscous it is, the more it doesn't want to flow. Kind of like tar, it's not easy to pour tar, but water is easy to pour. Well, we want to compare apples to apples in this case. So we want to compare hydrocarbons. So we have pentane, hexane, heptane, octane, nonane. So these are basically hydrocarbons. Pentane has 5 carbons, nonane has 9 carbons. They're a straight chain. We saw them on previous slides too. The molar mass is obviously going up here. So in this case here, if I wanted to judge the viscosity, pentane will have lower viscosity than nonane because the higher London dispersion forces here is going to make them more attracted to each other, and they're kind of like holding on to each other, not letting each other flow out of the container. So I like to imagine like all of these guys are like little molecules, and they're like, hold on to me, don't let go. Kind of like Titanic is turning over and then they're all falling down, but the stronger ones are holding on, so they're falling down slower. Okay, so that's viscosity right there. Has to do with intermolecular forces. In this case, we are judging based on London dispersion. Okay. Now, another way to break the viscosity to make it more less viscous so it flows easily is to actually increase the temperature. When you increase the temperature, what you do is you give the molecules more energy, and when they have more kinetic energy like that, they can overcome the intermolecular forces and then they can flow. Basically, you heat them up, they let go of each other, so they start flowing better. Okay, so that's common sense. So, I mean, you think about it, people heat up something that's like viscous and then it flows better. I would imagine like something like tar. See that. Okay, so they show you a picture here, viscosity of water versus temperature, and you actually can see that when they measure viscosity, it comes down as you heat it up. All right, the next one, so we've had surface tension, we've had viscosity, all has to do with intermolecular forces. Now we have capillary action. Capillary action is why your water can go up a straw. Okay, or any tube really. So under capillary action, we want to focus on cohesive forces and adhesive force. Adhesive is basically the attraction between the liquid and the surface of the tube. And cohesive is the liquid and liquid. So this is the intermolecular force right there. Well, not always intermolecular, but from one liquid to another liquid. Okay, a lot of times we are talking intermolecular forces, but I want to show you an example that has actually metallic forces holding it together. So that one says the narrower the tube, the higher liquid will rise. It's just because of the forces compared with the gravity. Okay, now let's take a look at capillary action and what a meniscus looks like. So this is your meniscus that we always see when we are doing any titrations or really measurements of any liquids. And well, we always have most of the time is water-based, so aqueous, right? Solutions. We always read the lower meniscus. So why is there a lower meniscus like that? It's concave because the adhesion force to the glass is stronger than the cohesion for itself. So if it's like just water, water is London dispersion not London dispersion, hydrogen bonding, right? Hydrogen bonding, remember, is a lot weaker than covalent bonding or other types of bond. So that's why it can be more attracted to the glass surface rather than itself, okay? Now, and then you take a look at this one. This is mercury. Mercury has metallic bonds that are attracted to each other. So they're actually bound together. So the cohesion is much stronger than adhesive force here. And that's why the meniscus of mercury is convex up like that instead of concave. So that's kind of cool. But if you see this, do not play with this. We do not use this anymore. Mercury is not allowed on campus, okay? But now we have like alcohol thermometers. Okay, so while we're at it, we finished talking about liquids. We had surface tension, we had viscosity, and then we talked about capillary action, and we talked about the lower meniscus versus the concave versus the convex. And then now we want to talk about the different phases. Okay, so the different phases here, for the first one, we want to talk about vaporization, changing phase from liquid to gas. To vaporize something, you need to give it energy, correct? So when you heat it up, then it will be easier for you to vaporize it, okay? And then another thing is the surface, the ones on the surface, remember they're less stable because they don't have bodies on the top covering them. So the surface molecules are going to be easier to be vaporized. So if you have a bigger surface area, like on a dish, on a plate, instead of just a small beaker, you would vaporize things a lot faster as well. So it depends on the surface area and the temperature, okay? So they show you here, the higher the temperature, the more of them evaporate. So you can see higher temperature, more of them can evaporate a lot of, the evaporation is speeds up, okay? So higher surface area and higher energy temperature. And then condensation is the opposite of vaporization. So we go the opposite direction from gas to liquid, okay? So because they are opposites, they basically are complementary, okay? So complementary in this case where if you take a look at the heat of vaporization, because you need to put heat in to vaporize something, so it's a positive sign, right? Endothermic or heat of vaporization. Condensation is the opposite because it's complementary. It's the opposite sign because it's the exact opposite process. So if vaporization is endothermic, condensation will be exothermic. That's why it's a negative sign. We just say condensation is the negative of the vaporization, okay? So we talk about that there, and it says here, the weaker the attractive force is, the faster the rate of evaporation. That's because, you know, they're easier for you to change phases when they have a weaker intermolecular force. Okay, so liquid that evaporate easily, we call them volatile. Liquids that don't evaporate easily, we call it non-volatile. So you want to remember vaporization is endothermic and condensation is exothermic. So while we're at it, we want to take a look at the vaporization energy. I want to show you how we can calculate it. So here's one problem that we can do together, just real quick. And then actually after that, I need to show you some examples. So it says here, let me zoom out a little bit. Okay, calculate the mass of water in grams that can be vaporized at its boiling point with 155 kilojoules of heat. So another thing is like, I want to show you that table that we just looked at. So this one says heat of vaporization of several liquids. So we have water, we have rubbing alcohol that's weaker, and then acetone and diethyl ether. You see how water is higher because it has, in this case, hydrogen bonding, right? And rubbing alcohol has hydrogen bonding too, so it's almost the same. Okay, anyway, so they're saying at this boiling point, see how at boiling point you take 40.7 kilojoules per moles. So 40.7 kilojoules to boil 1 mole of water. At 25 degrees, you need more energy. You use 44 kilojoules per mole to vaporize it. So at boiling point, it's easier because you have higher temperature and molecules have higher kinetic energy. But let's go ahead and write that out. So delta H vaporization at boiling point, that's given to us, okay? And you don't have to worry about memorizing that. BP is positive 40.7 kilojoules per mole. So if they say I have 155 kilojoules, you can find out how many moles of water that is, because you know that 1 mole can be vaporized using 40.7 kilojoules. Okay, and then based on that, you know also that 1 mole of water, if you look on the periodic table, is 18.02 grams of water. So once we have that, we get our answer in grams of water, 68.6 grams of water. Okay, so that was that. Now, I wanted to take a step back and go back to some questions that you might see based on all the different trends that we have seen based on boiling point, melting point, volatile or not, and maybe surface tension, viscosity, volatility, vapor pressure. Oh yeah, we're gonna talk about vapor pressure too. So let's talk about vapor pressure before we do that. So when we wanna talk about vapor pressure, it's basically, if you have this picture here, I'm gonna show you. So you have this flask that's closed. At first, when you just start, a lot of these guys are like, whoa, look, there's space here. Let's go ahead and vaporize and turn to gas right here. And once they turn to gas, they're like, hold on a second, it's getting a little crowded here. Why don't some of you guys go backwards? So there's going to be a reversibility of evaporation and condensation happening. Eventually, they come to a point where the evaporation slows down and the condensation picks up, so they're all the same rate. So rate of evaporation at this point will equal to rate of condensation. We call this the dynamic equilibrium, okay? Dynamic equilibrium happens after you let the processes kind of settle and they're happy and they move at the same rate and it looks like it's not changing anymore. It's really because they're moving at the same rate, so you can't see the change in the liquid level, okay? So that is called dynamic equilibrium. So the definition of vapor pressure is once you hit dynamic equilibrium, there's a certain fixed amount of gas in the flask here. And by the amount of gas you have, that's how much vapor pressure you'll have. The more gas you have, the higher the vapor pressure will be, okay? So while we're talking vapor pressure, something that's volatile will have a lot more gas molecules, agree? Something that's weak intermolecular force will have a lot more gas molecules, therefore will have higher vapor pressure, okay? So let's take a look at some molecule examples. So we were doing, we had some examples earlier, but I wanted to show you one that you might see kind of like on a test question, okay? So let's try one. We have BF3, we have NH3, and we have NF3. So we worked on some already earlier, but now this is the one we want to focus on, okay? So BF3 is like this. It's the one that's happy having just 6 for boron. And it's trigonal planar, it's 120 degrees. So this guy is nonpolar because they cancel each other out because they go opposite directions. Okay, because it's nonpolar, The bonds are polar, molecules non-polar. This only has London dispersion. Okay, let's look at NH3, what it has. NH3 looks like this. When you draw it out, it's tetrahedral, well, trigonal pyramidal, okay, because it's tetrahedral shaped with a lone pair. So I'm going to do this one is same with the page, that same with the page. This one sticks out, this one sticks back. Okay, and this one here is 109.5, well, less than 109.5. Okay. And so in this case, it's pointing up towards nitrogen, everybody gets. So this is the negative end, that's the positive end. So NH3 here has London dispersion. It also has dipole-dipole because it's polar, but not just that, it's actually the strongest type of dipole-dipole. It has hydrogen bonding. So that's the strongest one. I like to rank it by the strongest that it has. And then that way I can tell this one's going to have the strongest intermolecular force. The NF3 is going to look just like NH3, but instead of H's, you have F. Okay, so there's an F. And then there's an F sticking out, and there's an F sticking back. Okay, once you have this here, you're like, well, look, it's the same thing. Now, in this case, N is pointing downward. Everybody is pointing down. Okay, it's down towards the pyramid because it's a trigonal pyramidal shape. Like this. So it's these guys, okay? So NF3 and NH3 have the same geometry right there. It's trigonal pyramidal. So see how that one points down, NF3, everybody points down. So the molecule is polar. So it has London dispersion. And dipole-dipole. But it doesn't have hydrogen bonding because there's no NH, FH, or OH. This one does though, okay? So you can see how if you're ranking intermolecular forces, okay? So rank by increasing the first one, intermolecular force, IMF, okay? If we go from BF3 goes up to NF3, goes up to NH3, agree? That's increasing intermolecular force. Now, because it's increasing intermolecular force, we can increasing boiling point, same trend, right? Increasing melting point, it will be the exact same trend. So go ahead and write it. Boiling point, the lowest one will be a BF3, and then NF3, and then NH3. And then if I ask for a melting point, I could do the same thing, BF3, and then NF3, and then NH3. So I can ask you increasing, I can also ask you decreasing. I mean, just showing you variations of questions. So far we've ranked by 3 things. What about we want to rank it by increasing surface tension? So surface tension, remember, the higher intermolecular force, the higher the surface tension will be. So same thing, we have 3, NF3, and then NH3. Okay, and what if we want to rank by viscosity? Same thing, right? Viscosity is from lowest intermolecular force. The most viscous is the most highest intermolecular force. So BF3, and then 3, NH3. You're like, oh, all of them have the same trends. So if you see the connection there and how to rank, you can see who has the same trends and then who has the opposite trend. Okay, so now these are the ones that we covered. So we were talking melting point, boiling point, surface tension, viscosity. Let's talk about volatility now, okay? So volatility is basically the higher the intermolecular force, the least volatile it will be. The highest one is the least volatile. So in this case, ammonia, NH3, will have the least amount of vapor because it's strongest intermolecular force, so it's harder for them to turn to gas. NH3, and then NF3, and then BF3. So you see how this one's the opposite, right? What else can you think of? EFG. The next one is increasing vapor pressure. So increasing vapor pressure, again, vapor pressure, something that has very few gas molecules will have lower vapor pressure. So you have NH3 as the lowest vapor pressure because it has the strongest intermolecular force. And then NF3, ooh, I wrote it wrong, NF3, and then you have BF3. Okay, so just showing you that I can just give you a series of molecules and I can ask you any of these trends. And I can ask you increasing or decreasing. Okay, so just keep that in mind. And with that, we can keep going because we were talking about vaporization, right? So I want to show you something here. So we were talking about how, like, if you increase the temperature, it's easier to vaporize. And if it's easier to vaporize it, your vapor pressure would be increasing. Agree? So I want to show you a picture of a graph here. It's a vapor pressure curve. And this can be for, we can talk about it for water in this case. Okay, so this is temperature. This is vapor pressure. Okay, and then we can measure it. So we're saying that when you have any liquid, if you increase the temperature, it'll be more vaporization happening. So then you'll have a higher vapor pressure because there's more gases. Okay, so I wanted to show you this here is the vapor pressure curve. The higher the temperature, the higher the vapor pressure will be. That's called the vapor pressure curve. On this vapor pressure curve, if you see in this case, okay, so that particular point here, let's say we are always at 1 atm. So once you hit your vapor pressure of 1 atm, so the vapor pressure is 1 atm and our environment is 1 atm, agreed? Okay, and then you come down here for water. If this is water here, what's the temperature over here? This will be 100 Celsius. Okay, so basically that's on the vapor pressure curve, you can find a boiling point. Now, boiling point is defined as this, okay? So boiling point, I'll write it out. Boiling point, boiling point is the temperature where vapor pressure of the liquid equals to the external pressure. So because we are at 1 atm, right? We are at 1 atm. So if my vapor pressure hits 1 atm, it's the same as my external pressure. That temperature that happens there is my boiling point. So boiling point is the temperature where your vapor pressure of the liquid equals to the external pressure. That's for, so in that case, what if my external pressure is 2 atm? Well, then you look for 2 atm and then you find a boiling point. It's a different number. If your vapor pressure is half atm down here, then it's a different number. So the temperature of water, boiling point changes depending on what external pressure is. Okay, so because 1 atm is so common for us, we actually defined it as normal boiling point pressure. Normal boiling point means the temperature where vapor pressure of the liquid is the same as external pressure of 1 atm, or we can say 760 torr millimeter mercury, same. Okay, so in fact, this guy here at 100 degrees is so common because it's at 1 atm for water. We define that as our normal boiling point. If you want to do one at half ATM, whatever this temperature is, this one here, this temperature, this is a boiling point. It's not a normal boiling point because it's not 1 ATM. Only 1 ATM is called normal boiling point. Okay, any other pressure, you just call it boiling point. So that's for 1 ATM. All right, I want to show you a cool chart here. Okay, so this cool chart here tells you boiling point is where the temperature, vapor pressure of the liquid equals to the external pressure. Normal boiling point is 1 ATM. Now, and then when you're not at 1 ATM, you don't call it normal boiling point, you just call it boiling point. So what's cool is when you climb up to Mount Everest, the ATM, the pressure, remember how when you go up in higher atmosphere, the air is thinner, there's lower atmospheric pressure. So your boiling point is actually much lower. You can boil water at 78 degrees Celsius instead of 100, where we are. Okay, we're at sea level, so we're 100. And then you go to Denver, you boil at 94. You go to Mount Whitney, highest mountain peak in 48 states, cool, 87. And then Alaska, it's 83. And then Everest is even lower. So that's pretty interesting. Okay, so these guys here, the ones that are not at 1 ATM, what do you call them? These are just boiling points. The one at 1 ATM is called the normal boiling point. So you can call the 1 ATM as normal boiling point, and then there will be a normal melting point as well, because it's at 1 ATM. Okay, so that's that. Now, while we're looking at it, let's take a picture of, take a look at this picture here. So here's my vapor pressure curve for a bunch of different kinds of liquids. Okay, and they're saying which one has the strongest intermolecular attraction. So the strongest one should have the highest boiling point, agree? So where's the, we can just basically look, okay, let's say we want to look for 760, somewhere around here. So this one right here, I guess I could draw a line, show you. That's around 760, okay? Anyway, so this guy here, the first line will boil at like 30 something degrees Celsius, and this one doesn't boil to 130 something degrees. So obviously the last line here, whatever the color represents, I think it's TiCl4, is going to be the one that has the strongest intermolecular force because it boils at the highest temperature. Okay, now the next one we want to take a look at, we have another similar question. It says here, which one is the most volatile? Well, the most volatile with the one that's the lowest boiling point, right? So the first line in this case would be the most volatile. In this case, it should be ether, that color for ether. Okay, now, and then here's the picture here on slide number 41. You can see where the normal boiling point is, where you have 1 ATM, 764 millimeters mercury, and whatever the temperature down here, when you plot it down here, that temperature is the boiling point. So ethanol boils at 78.3 at 1 ATM. And then diethyl ether is 34.6 at 1 ATM. So if you ever spill ether, you're going to be smelling a lot of it because it's going to be in vapor phase. All of it is going to be in vapor phase. Water, not quite. You have to like actually work a little harder to vaporize it. Okay. So now that we have that, oh yeah, there was another question I wanted to show you. So what if I have all these mountains, okay? And then when we fly on an airplane, we fly above the highest mountains, agree? We're not going to run into the mountains, so we fly higher than them. So what's the boiling point on the airplane? Remember, the pressure in the cabin, I mean, the air in the cabin is pressurized. The cabin is pressurized to be typically at a regular pressure. I don't really know what the pressure is, but it is pressurized, so it will not be changing. They try to keep it close to 100 still. Okay, so just keep in mind, if you're in a pressurized cabin, it's not going to change the boiling point because it's at the correct pressure of 1 ATM still. Okay. All right. And the next thing we want to talk about is we talked about phase changes. Now we want to talk about the energy required to heat and change the phase, okay, or change the temperature in the phase. So in this case here, we were talking about changing phase like vaporization from liquid to gas. We call this process here phase change, we call it vaporization, and we call it boiling. And then before it hits the boiling point, down here, if you just add heat, all it does is raises temperature. Once you hit the phase change, it flatlines, doesn't change temperature until everybody is changed from liquid to gas, and then the gas phase increase in temperature again. So basically, they can't multitask. They can only do one thing at a time. They can do temp change, or phase change at a time. So if you ever had to calculate the energy for a temp change, you use Q equals MC as delta T. Phase change, we would use what we just did earlier in this problem before this. We use delta H vaporization to calculate it, okay? So we know how to calculate, and they'll ask you, so sometimes they'll ask you to calculate what's the temperature what's the energy needed if you want to raise your water from 20 degrees Celsius and then into a gas at 140 degrees Celsius. Then you say, well, I got to do this step, raise the temperature to 100, and then I have to change all of it to gas phase, and then raise the temperature from 100 to 140 in gas phase. Okay, so we'll be doing calculations on that. So let's take a look at the phases. Well, we'll do more phases first, then we'll do calculations. So there's one thing that's cool, it's called supercritical fluid. Supercritical fluid happens when you increase the pressure and the temperature so high, at some point it's like, it doesn't know whether it needs to be gas or liquid, it turns into supercritical fluid. So if you Google it, you can find videos of how some people on YouTube actually got some dry ice and they turn the dry ice into supercritical carbon dioxide, which you can use to decaffeinate tea and coffee. It's kind of cool. All right, so we'll talk more about supercritical fluid. It exists past the temperature that's critical temperature and a critical pressure. It has to go past a certain temperature and pressure. And whatever the number is, that depends on the type of chemical you're talking about. Is it carbon dioxide? Is it water? Is it something else? That all depends, okay? So let's see. So we were talking about boiling, vaporization, and we want to talk about sublimation. So sublimation is when you have solid turning into gas. Deposition is the opposite, gas turning back into solid. Remember, this is endothermic, this one is exothermic. And then we have fusion, which is kind of the same as fusion is melting. It's similar to what we just saw for vaporization or boiling, right? So if you wanted to change the temperature, say I have a piece of ice at -10 Celsius, I want to go ahead and how much energy will it take for me to heat this piece of ice until it reaches like 35 degrees Celsius, okay? And then you say, well, there's 3 steps. I have to do a temp change, and then I have to do a phase change, and then I have to do another temp change after all the phase change is complete. So you have to do 3 separate steps. And remember, this is Q plus MCS delta T, Q plus MCS delta T, because there's a delta T there. But phase change will be, you take the amount times the delta H of the phase change, which is in this case, delta H of fusion, okay? So delta H of fusion will be an endothermic number, a positive number, kind of like the boiling. And then if you were to freeze the opposite, it will be exothermic, okay? So I'm gonna show you the numbers here we have for fusion. So for fusion, so we can just look at water. It says here 6.02 kilojoules per mole. So you remember for water, it was like, to boil it, it was 40.7 or 44, depending on the temperature, right? Kilojoules, and to melt it, it only takes 6. So it's a lot less energy for you to melt something than for you to vaporize it. Why is that the case? Because to melt something, all you have to do is move the molecule from one distance to another, just separate a little bit. For you to turn liquid to gas, you have to put a lot more energy because they have to go so much further apart. They have to separate the intermolecular forces a lot better. So it's easier to melt something than it is to vaporize something, okay? So remember, when we want to freeze it or crystallize it, it's the opposite sign of fusion, because fusion is endothermic, crystallization will be exothermic, a not negative sign. And then if you want to talk about sublimation, it's you just combine the fusion and the vaporization number. And if you want to do what was the other, the opposite, where you want to go from gas to solid, you just take the negative of vaporization and negative of fusion, because it's the opposite process. Okay, so you will need these because sometimes you'll have to calculate heat of phase changes. So that's important to know, like you have numbers for fusion, you have numbers for vaporization, you have numbers for crystallization, sublimation, vaporization, condensation, and you got to know who's opposite of who. Fusion and melting. Fusion and melting is the opposite of freezing or crystallization. So is vaporization opposite of condensation. Okay, and then they say sublimation is the total of fusion and vaporization. So they show you a picture here. Heat of fusion is a lot smaller than vaporization. We just observed that also from our chart anyway, because it's a lot easier to separate molecules to solid to liquid than it is from liquid to gas. All right, so now we want to get fancy here. We want to go ahead and say, how much heat do we need to convert? I'll write it out. We want to start doing, so we did, like, we saw the chart for fusion, we saw the chart for vaporization. I want to do one that has all of it together. Okay, and then we'll do, that's too much for this. Okay, that's good. Okay. Question is, how much heat or energy do we need to convert 1 mole of water, H2O, we meant to say water, this is actually going to be nice, from negative 25.0 Celsius to 125.0 Celsius. Okay, now what you need to know, if it's for water, I will not tell you the melting point and boiling point of water. Do you know what it is? Okay, I'm going to go and write it down. That's by default. Okay, what's the melting point of water? Melting point of water is 0 Celsius. What's the boiling point of water? It's going to be 100. And that stuff, you got to know this. Now, what they will give you is they'll give you CS of solid H2O. They'll give you that. They'll say this is 2.09 joules per gram Celsius. They'll give you that, okay? This will zoom in a little bit so you can see better. And then you have CS of liquid H2O is 4.18 joules per gram Celsius. And then you have CS of gas phase H2O. It is 2.01 joules per gram Celsius. Kind of close the gas and the solid, huh? Okay, so and then you have delta H fusion. We talked about it, it was 6.02 kilojoules per mole. And then you have delta H vaporization, it was like 40.7 kilojoules per mole, because we're going to vaporize it at boiling point. Okay, so we know this one will be given to you. No matter what chemical it is, this will be given to you. If it's water, they expect you to know boiling point and melting point. The standard number is 0 and 100 degrees Celsius. Okay, and if it's a different compound, they will also give you the melting point and boiling point for that compound. Now, let's go ahead and consider how many steps do I have. So before this, I was showing you 2 separate pictures. Let me show you the picture again. Remember how we said there's fusion and there's 3 steps here, and then I showed you another one of boiling, and there's another steps there. So now we gotta decide how many steps I have in this picture here. Okay, so if I have something that's negative 25 degrees, what phase is that? It's going to be solid, right? When is it going to stay solid? It's going to stay solid until I hit 0. Agree? So it's going to stay solid until it hits 0. And then does it stay 0 after that? No, you keep heating it up, and then temperature goes up from 0 all the way to 100. Okay, it goes up from 0 to 100, and then it changes phase from liquid to gas at 100. And once it changes all to gas at 100, it can go up in temperature again to 125 degrees Celsius. So I want to show you what it looks like, okay? So the first temperature I want to consider is negative 25 Celsius. It's a solid, and I know it's going to stay solid. It's going to go up in temperature until it hits 0 Celsius, and then you go from solid, and then it changes all to liquid. Okay, once it does all that phase change, so this is going up in temperature, so delta T up here, and then phase change. And then once you go through the phase change, it goes up again all the way to 100 degrees by doing a delta T. Now this one here is in liquid phase, right? Because everybody turns to liquid, and then it heats from 0 to 100 at liquid phase. And once you hit 100, you start turning into another phase, right? Liquid going to gas. Okay, and you're like, okay, once you hit gas phase, then you can go up in temperature as gas over here. Okay, so there's all kinds of stuff happening. So I want to go ahead and draw it out on a chart here. It's easier to see. There's a lot of steps. So, but I do want to highlight. So all you got to do is remember I'm not going to do it to scale. So this is negative 25. And then there's 0. And then there's 100. And then there's 125. Those were the temperatures it was on the question, okay? So in this case here, I know at first at 25 degrees, I'm going to heat it up. It's going to hit 0 degrees Celsius. This is all going to be in solid phase, and it's going up in temperature until it hits 0. And then once it hits 0, I'm going to change from solid phase to liquid phase at 0 Celsius. Once everybody's converted over, it's going to go up all the way in temperature to 100 degrees. This is in liquid phase, right? And then once you hit 100, you do your boiling. You go from liquid going to gas. Notice I did a longer liquid to gas and solid to gas because it's going to be harder for you to turn liquid to gas than it is solid to liquid. So, and then once you turn everybody to gas, you can go up in temperature until you hit 125, and this is in gas phase. So you see how there's 2 phase changes and the 3 delta T changes, okay? And each delta T has a different phase, solid, liquid, and gas. So this is step 1, this is step 2, this is step 3, step 4, and step 5. So earlier we only had 3 steps, and this one you have 5. So let's go ahead and calculate the heat for each step. Remember, whenever you have temperature change, you use Q equals MCS delta T. When you have phase change, you use the vaporization or fusion number. Now, if they ask you for a cooling problem, if they give you the cooling problem and give you the fusion and vaporization, remember the condensation and freezing is going to be the opposite sign but same numbers, okay? So step 1, I'm going to write it down. So Q1 equals to MCS delta T, okay? So what's my M and CS? My CS for solid, I have to write 2.09 joules per gram Celsius. And then my delta T is from final minus initial. So final is 0 minus initial of negative 25. And then my M here is mass of 1 mole. I guess I'll go ahead and write the molar mass here if you don't remember. H2O is 18.02 grams per mole. So if it's 1 mole, it will be 18.02 grams right there. Okay, so you put that together, you get your answer in joules, you get 941 joules. So I'm going to go ahead and change it to kilojoules, okay, 0.941 kilojoules, because my next step is going to be in kilojoules. I'm just going to convert them all to kilojoules, okay? So that's 1. So a lot of times people forget to convert and then they add the kilojoules and the joules together, but forget the different units and you get the wrong answer. So you want to be careful. So that's the first step. Now let's take a look at the second step. Second step is melting infusion here. And we're going to take 6.02 kilojoules per moles there. And then it's 1 mole. So Q2 is 1 mole. It's N times delta H fusion, basically. So 1 mole times 6.02 kilojoules per mole. So the answer is 6.02 kilojoules. Okay. All right. Step 3 is Q equals MCS delta T. So Q equals MCS delta T. Now, which CS are we going to use now? It's liquid phase. So you have to get the liquid CS, which is 4.18. So I'm going to go ahead and do that. So 18.02 grams, 4.18 joules per gram Celsius. And my temperature change is final minus initial, so 100 degrees Celsius minus 0 Celsius. Okay, that's going to give me 7.52 times 10 to the power 3 joules. And if I needed to convert to kilojoules, just divide by 1,000, so it's 7.52 kilojoules. So that's for step 3. Then when we continue on with step 4 here, step 4 is another phase change, but this time it's vaporization. So we'll use 40.7 kilojoules per mole. And Q4 is 1 mole, so N times delta H vaporization. So it will be 1 mole times 40.7 kilojoules per mole. And the answer is 40.7 kilojoules right there. And then let's take a look at step number 5. Step number 5, you're 1 mole, you're going up from 100 to 125 degrees. So Q5 equals to MCS delta T. So you remember every time you have a temp change, you use the Q equals MCS delta T. Every time you have a phase change, you use N times delta H or whatever process it is. Okay, so in this case here, 18.02 grams again, CS for my gas phase, if you take a look, it's given as 2.01. So 2.01 joules per gram Celsius. And then my temperature change is final minus initial, so 125.0 Celsius minus 100 Celsius, okay? And I'm gonna get, in this case, 904 joules. So that would be equal to 0.904 kilojoules. Now my job here now, the heat is needed is Q1 plus Q2 plus Q3 plus Q4 plus Q5. Add them all up together, you get your total energy that's needed. And I get 56.085 kilojoules. So really, we're going to only be keeping 1 decimal place here. Okay, so 56.1. That's how much energy you need in kilojoules. So let's try another example here, but now instead of using water, you'll see different examples as well when you're doing homework in dynamic study modules, quizzes and exams, practice exams anyway, okay? And you see on the test after you practice. So here's one with, instead of water, we'll do it for benzene, which is C6H6, okay? So the question is, how much heat in kilojoule is needed to raise the temperature of 12.0 grams of benzene C6H6 sample from -10 degrees Celsius to 25 degrees Celsius. So they gave you the temperatures they're interested in, and then I'll give you all the specs on benzene, okay? So for benzene, we have CS for solid phase, 1.25 joules per gram Celsius. And then CS for liquid, 1.70 joules per gram Celsius. CS for gas phase is 1.24 joules per gram Celsius. Okay, and then we have melting point given as 5.5 Celsius. boiling point of 80.1 Celsius. And then we have delta H vaporization of 30.9 kilojoules per mole. Delta H of fusion is giving us 9.8 kilojoules per mole. And then molar mass is given as 78.11 grams per mole. Okay, so that's all the information I'll give you on benzene. So let's go ahead and try to draw a picture out. So I'm seeing I have to go from -10 to 25. At -10 is going to be solid. Just go up in temperature all the way to 5.5, and I'll stop there and change phase from solid to liquid. And then after it changes solid to liquid at 5.5, it's going to go up again to 25 degrees. Really can go up to 80.1, but we're stopping at 25 for this problem. Okay, so I'll see there's a lot less steps here. Let me go ahead and draw it out, okay? So I'll draw it out. I like to basically mark down, so I have -10 Celsius, and then it's gonna go to 5.5 Celsius, and then it's gonna go to 25 Celsius. It's not to scale because I'm not really a good artist like that, so you guys would just have to put up with it. So this is heat added in kilojoules. Okay, so when you add heat, at first you start -10 to 5.5. This is going to be in solid phase because it hasn't melted. Once it hits 5.5, it will melt from solid to liquid, and then it will go up in temperature as a liquid to 25 degrees Celsius. So there's only 3 steps, 1, 2, 3. So remember, these two going up in temp are going to be Q equals MCS delta T. This one here will be N delta H, in this case, fusion. Okay, so Q1 is MCS delta T. So what in the world is my CS? My CS is for the solid. So it's going to be 1.25 joules per gram Celsius. And because I see grams here, I'll put 12 grams of benzene here. And my delta T is 5.5 minus -10. So 5.5 Celsius. Minus -10 Celsius. Okay, and then you get 232.5 joules, or 0.2325 kilojoules. Okay, so let's keep going. We got the step 2 is N times delta H fusion, which N here, we get the molar mass and we have 12 grams of it. The moles is 12 grams over 78.11 grams per mole. Agree? So that's how you can get moles of benzene. And then delta H of fusion will be, in this case, given as 9.8 kilojoules per mole. Okay, so my answer over here you're going to get is 1.51 kilojoules. And then let's keep going to step 3. Another Q is MCS delta T. But this time my CS is for liquid phase. So if you take a look at the liquid, it's going to be 1.7. Earlier it was 1.25 because it was solid. So another problem is people always use the wrong phase. So just make sure you're using the correct phase, okay? So this one's the liquid phase, so 1.70 joules per gram Celsius. My delta T is from 25 degrees Celsius minus 5.5 degrees Celsius. Okay. And then my M here is 12 grams. Okay, so let's put that in together. You get that as 397.8 joules, which is 0.398 kilojoules. And then you add them up. Q total is Q1 plus Q2 plus Q3. Ends up being not that much, 2.1 kilojoules. Okay, so that's how you would do this problem here if it's for benzene. Now remember, they will give you the melting point and boiling point for these guys, but for water, they expect you to remember what the melting point and boiling point for water is, okay? So So we're there, and now we want to talk about the something that's cool called the phase diagram, where you can actually see where the supercritical fluid will exist on the phase diagram. So first of all, you're like, okay, what in the world is a phase diagram? So let's start with what we already know so far, okay? So I want to go ahead and draw it out. So phase diagram is just basically going to be pressure versus temperature. So whatever pressure versus temperature. Now what we learned earlier is like when we heat up the temperature, the vapor pressure goes up, right? And it was pressure versus temperature. So that's my vapor pressure curve right there. And remember, on my vapor pressure curve, I can find boiling points. Remember that? So that's my vapor pressure curve right there. And then let's say if we wanted to do a boiling point at, let's say 1 atm. You would do dot, 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 dot. Oh, not straight dot, but. Okay, and then go down here. This one, if it was water, it would be 100 degrees Celsius. Remember that? So that's the spot here where you get a normal boiling point for water. Okay, so there's this line here when you were boiling. What's crazy is, take a look at this picture here, okay? You are literally increasing the temperature, and as you increase the temperature, it shows you when it starts to boil at 100 degrees, because that's when it changes phase. So this line here actually tells you, because it changes phase, it's a divider between liquid phase and gas phase. Okay, so we can see here, as you increase temperature, eventually it hits this point here and it will start to boil and it'll turn to gas phase. So that's the line between the division between liquid and gas. And then you have another point that divides, in this case, solid and liquid. Okay, so solid and liquid is divided by another line, and then you have another line dividing solid and gas. So that's what the phase diagram looks like. It tells you what region. If you say this region, this is the gas. If you on this line here, that's liquid and gas exist together, because it's a line where you can find boiling points. Okay, so if this is the line where you can find boiling point, what is the line dividing solid and liquid? This is the line where you can find the melting point or freezing point. So in this case here, this one here would be 0 degrees Celsius for water. Okay, so this is the melting point, and that's the boiling point right there. So if you took a look at this chart here, you can actually describe a process what we just did earlier. That we were saying, how much energy do you need to heat up from -25 Celsius, keeping the pressure the same? So pressure is at 1 atm, okay? We're going from -25 all the way to 125, and you can see the phase changes here. -25, temperature up, temperature goes up, temperature goes up, temperature goes up, phase change. In this phase here, on this dot here, solid turns to liquid. Solid and liquid exist together on that spot, and then in temperature change increase again. Only liquid phase exists here, and then boom, over here, liquid and gas exist together. And then after everybody turns to gas, it crosses over into gas phase and increased temperature again. So you can see the heat curve that we just saw on this line on the phase diagram, okay? So on the phase diagram, we saw the line dividing between solid, liquid, and gas. So this is the line where if you cross this line, it turns from liquid to gas. If you cross this line, it turns from solid to liquid. If you cross the bottom here, it turns from solid straight to gas. You can go backwards. You can go backwards. This is condensation. This one here, if you cross from solid to liquid, it's melting. Liquid to solid, it's going to be freezing. And then we talked about supercritical fluid, right? So there's this point here above a certain pressure and temperature at this critical point that contains critical temperature and pressure. So this would be the critical temperature, and that would be the critical pressure right there. Anything above this line right there is supercritical fluid. That's where it exists. Okay, So I'm going to show you, because my drawing is not that good. We got slides I can show you from. So this is the line phase diagram for water. It's a small one. I'm going to show you a bigger one, bigger picture, okay? So right here. So this picture on slide number 20, right here, you can see here, we talked about at 1 atm, you can find a normal boiling point on this point, normal melting point, right? If you wanted to do not normal, a different atm, just go lower pressure or high pressure, whatever it is, you can still find the boiling point on this line here, okay? So crossover is vaporization, cross the other way is condensation because it's a line dividing liquid and gas. Okay, and that's our vapor pressure curve, right? Critical point above it right here, you get supercritical fluid. Okay, and then fusion curve right here, the line that divides solid and liquid is called the fusion curve because this is a vaporization curve. So fusion curve, you cross over, you melt, and then you go backwards from liquid to solid, you're freezing. You can find a melting point from that spot in the line. And remember, on this line here, solid and liquid exist in two together in equilibrium. On this line here, liquid and gas exist together. And on this line here, solid and gas exist together because it's sublimation crossing over and deposition the other way. So this one is called the sublimation curve. Now, what happens to this line, this spot here called the triple point where all these three lines meet? Triple point is where all three phases exist together in equilibrium. That point right there, you can find solid, liquid, and gas at the same time. How crazy is that? I would love to see that point. Maybe there's videos of people doing those experiments and can look up. Okay, so that's our phase diagram here. So based on that, let's go over some few questions. So before that, we were talking about how if you're going over here, remember we say we cross over here is literally keep the pressure at 1 atm, regular pressure. We go from a low temperature, it was in solid phase, and then it melts once it hits this temperature. And then after it's done changing phase to liquid, it goes to the liquid region and it goes up in temperature because the temperature is increasing over here. And then it hits to the boiling point right there on this line. And then it changes everybody to gas phase, and then you can increase temperature again. That's why this is gas. Now you can do the same thing. Instead of keeping pressure the same, why don't we keep temperature the same at 25 degrees Celsius? We keep 25 degrees Celsius, but we change the pressure. So at first, at 1 atm and 25 degrees Celsius, you have liquid, and then the liquid will drop in pressure all the way until this point here. And then this point here, the liquid will turn into gas because the pressure falls so much, it turns to gas phase. Okay? So that's how you can read a phase diagram. Now, I want to show you, this is where it gets difficult. Okay, I'm going to show you this picture here, and I'm going to ask you what phase it is by reading what's underneath and covered. Okay, so the first one is 20 degrees Celsius, 72.9. Oh, you can see what I see. And never mind, I'm just going to, oh yeah. 20 degrees Celsius, 72.9 atm. Okay, so 20 degrees Celsius, where's 20 degrees? Somewhere here, 72.9. It's somewhere in this region, right? So what phase is that? It's going to be in liquid phase, okay? And then let's take a look at the next one, 56.7 negative Celsius and 5.1 atm. So negative 56.7, 5.1 atm right there. This is triple point. So all three phases, solid, liquid, and gas, exist together, okay? And the next question we have is 10 Celsius, 1 atm. 10 Celsius, 1 atm is in this region here. So if this is solid, liquid, this must be gas phase, okay? So that one was gas. The next question is negative 78.5, 1 atm. Negative 78.5, 1 atm. So this point right here, this one has solid and gas existing at the same time, okay? In fact, as you cross this process going from here to here is actually process B is called sublimation because it's changing from solid straight to gas at 1 atm. So this is for carbon dioxide. Also, this is a dry ice phase diagram. That's cool. So at 1 atm, we are at 1 atm. That's why you only see dry ice turn from solid to gas. You never see liquid carbon dioxide, right? When can you see liquid carbon dioxide? Well, you gotta go up higher than 5.1 atm and be in this region here. And a lot of times, once you go up that high temperature and pressure, you can get to this point up here. That will be where you find supercritical fluid carbon dioxide. Okay, so those videos are really cool. I want you guys to look it up. Okay, the next one is 50 degrees Celsius, 80 atm. 50 degrees Celsius is somewhere here. 80 atm is all the way up here. That's where you find supercritical fluid. Okay, so that's for carbon dioxide. And you can see there's other kinds of phase diagrams they have for like carbon, they have for water, carbon dioxide. Really cool stuff. You can look it up. And there's even phase diagrams for ice. There's different kinds of ice that can be formed depending on pressure and temperature. It's really crazy. So water's phase diagram that we just saw was just, we'll go back to water. Just a small part of it. So this one was water, right? So under the solid here, there's so many more lines here telling you different kinds of ice that can be formed. It's really cool, okay? So the next thing we want to talk about after phase diagram is talk a little bit about crystalline structures, crystalline solids, because we finished liquids, we were talking intermolecular forces, now we want to focus on solids. So when we want to talk about solids, there's only a little bit of crystalline solid I want to talk about. Crystal lattice is in the crystalline solid, you have unit cell, which is the smallest repeating unit, and it repeats itself, right? Each particle in the unit cell is called a lattice point. So there's something called lattice energy. We don't focus too much of it, but lattice energy is energy that's released once you combine the ions in gas phase to form solid. It's just a definition. So like if you take the ions in gas phase and combine them into solid, they should lose energy from gas to solid. So the amount of energy that they lose is called the lattice energy. Okay, lattice energy is bigger when ions are small but highly charged. Okay, small ions can bond closer together, so they're more stable, lower energy. So you end up releasing from gas all the way down to the bottom, more stable value. So it's bigger lattice energy. Highly charged will give you a stronger bond, so it's also more stable. So it will give higher lattice energy as well. Now, under crystalline structure, I only need you to memorize 3 things. The first one is simple cubic unit cell, is where you have 8 atoms on 8 corners, okay? And 1/8 of each atom is inside in your unit cell. So inside a unit cell, you only have 1 atom per unit cell, and you have coordination number of 6. That means each atom here has 6 friendly neighbors around it, okay? So you gotta memorize what a simple cubic looks like, how many atoms are in each unit cell, and what the coordination number for a simple cubic unit cell will be. A simple cubic unit cell is the simplest one, coordination number is 6. Body-centered cubic unit cell is kind of like a simple cubic cell, but there's a body-centered atom in the middle. So instead of just 1 on the outside like this, plus 1, you got 2 atoms per unit cell, and your coordination number here will be 8. So you need to know what they look like, what the coordination number is, and how many atoms per unit cell. You don't need to do any calculations with it, okay? You might see some on your extra credit, but not for credit stuff. All right, so face-centered cubic is the 3rd one, where instead of being in a body or nobody in the middle, now you have 1 on every face. So on every face here, you have half an atom, and there's 6 surface here. So 6 faces. So if half of it is 6 spots, you have altogether 3 on the inside, and plus the purple ones is 1/8 times 8. So you have 3 plus 1, you get 4 atoms inside the unit cell, and the coordination number for this guy is 12. So here's a summary of it. So you gotta remember what it looks like, how many atoms per unit cell, and the coordination number. You don't need to worry about these terms in the back here. Just like this stuff, you don't need to worry about, okay? All right, so that's for crystalline solids. Now, while we're talking about solids, I want to talk about different kinds of solids there are. We're not really doing a lot in chapter 13. That's why I combined 12 and 13 together. So we want to talk about the different kinds of solids that we have under crystalline solids. So we have molecular solids, ionic solids, and atomic solids. So molecular solids are made of molecules. And what holds molecules together? Intermolecular forces. Therefore, because intermolecular forces are in general weak compared to covalent bonds, ionic bonds, they have low melting points. Even anything with hydrogen bonding, like ice, is still low melting point, right? I mean, ice melts at 0 degrees Celsius. So compare that to ionic solid, where ionic solids are held together by ionic bonds, electrostatic charges, so you'll have higher melting points, okay? That's like trying to say, what's the melting point of NaCl? Really high. You can dissolve it, but can you melt it? You're gonna have to heat up really, really high. Okay, so atomic solid is where you just have atoms in there, and under atomic solids, we have different kinds of atomic solids. So you have non-bonding atomic solid where you have noble gases held together only by London dispersion. So they're super, super low melting point, even lower compared to some of these molecular solids, okay? Because non-bonding have no interactions other than London dispersion. So metallic bonds here are held together by metallic bonds. That one is a variable. So it's a little all over the place. So a comparison would be if they asked you which one's lower melting point, non-bonding or metallic, then you always say non-bonding is the lowest. Okay. On the other hand, network covalent is going to be the highest melting point because it's covalently bonded. So like diamond, in this case, quartz, silicon dioxide, held together by covalent bonds, super high melting point. So all you need to do is be able to rank them by melting points depending on what solids they are. Molecular solids are held by intermolecular forces, remember, generally low melting point. Ionic solids are held together by ions, so it's generally high melting point. Under atomic solids, we have non-bonding. They're usually really weak, so low melting points, only London dispersion. Metallic bonds kind of vary, it depends on the metal. There's some metals that you can hold and it will melt in your hands. And there's some you have to heat it up to like really, really high temperature. So that one varies. Network covalent solids are basically the ones that are bonded by covalent bonds, and it's going to be really, really high melting point. So example here is diamond, and then they showed you quartz earlier, and also graphite. So graphite is weaker than diamond because graphite is covalent bonded on 2D. And then from the one sheet of 2D to another sheet, it's intermolecular force. So it's a mixture of intermolecular force and covalent bonding. This one is all covalent all throughout. So diamond will definitely have a higher melting point there. Okay, so I wanted to show you, I'll list out a few solids here and you tell me which one is higher melting point, okay? So pick the highest melting point. So the first one is KCl and SCl2 for these crystalline solids. Okay, KCl, SCl2. SCl2 is all non-metal, right? So this is molecular. This one is ionic because KCl is ionic. So ionic is going to be higher than molecular for melting point. Okay, now let's take a look at B. The first option is carbon, graphite. So that one is the covalent network atomic, right? And then you have S8. This is a molecular solid. So in this case, because this guy is covalently bonded, that one will be a higher melting point. So I should write down atomic network covalent. Okay, now the next one is krypton versus potassium. This one is a metal, agree? So metallic, solid. This one is non-bonding atomic because it's a noble gas. So which one is a higher melting point? This one's going to be the lowest. So metallic will be higher than that guy. Okay. Now another option is you have SrCl2, which is ionic, and compare it to SiO2, which is quartz. And this one is atomic covalent network. So if you have ionic atomic covalent network, you're going to go ahead and pick the covalent network. That one will have the higher melting point. Okay, so sometimes you'll see questions to ask you to rank melting points. Sometimes they ask you pick highest, sometimes they'll ask you pick lowest. You just have to be able to tell when you're comparing them, which one would have a higher or lower melting point for these crystalline solids. And that is all we're going to cover for chapter 12 and 13. This is the end of the material. You guys made it. Congratulations. Now you just have to study for the final.